started.
Yeah, but nobody's here.
Count me in.
I don't know how to teach. Okay, if you're watching the video, nobody's here, except for one person, so I'll wait until somebody shows up. It's strange talking to you.
Strange.
Yeah. While we are waiting, what do you know about turbulence modeling?
We actually try to. We have many models like Reynolds stresses and.
Yeah, but do you know
runs.
physically what's going on and what these models are trying to do?
In real life, we are trying to actually approximately find the turbulence. It's a kind of chaos that we are trying to model with mathematical equations. And
yeah, but it still sounds a little vague and conceptual. Do you know exactly, if I said model turbulence for me in a simulation, would you know what to do?
No.
Okay. So yeah, I will talk about that today.
Probably approximately try to find the small particle.
In a way, yes, true.
We call this scale.
Scale?
Scale. I mean, we have a rank scale that we are trying to resolve the turbulence.
Yeah.
That's what I'm gonna do if you ask me.
Okay. Yeah, I mean, that's roughly what it's supposed to do.
This is why I came today. You know, you told me 2 weeks ago, last week. Okay. You talked about ILES, LES, and so on.
You want to learn about turbulence modeling?
What?
You want to learn about turbulence modeling?
Well, they were wondering, are you giving an exam?
No. Who was wondering?
The bridge, because you haven't started.
Oh, yeah, I'm waiting for one more person to show up.
Okay. Okay. They just wanted to make sure.
Okay, thanks.
They will never come back.
Yeah, somebody might come 10 minutes later. But some people have a dissertation presentation. No, thesis presentation. So.
Not today.
Yeah.
I mean, not from us here now. I checked the schedule.
Yes, from us. I have to go to one today.
I know it starts at 2.
2:30. Okay. I will tell you quickly about turbulence modeling. But first, let me show you the project, which you have obviously finished.
The last project you submitted, right?
Have you looked at it?
Yes.
Okay. Does it make sense?
Mm-hmm.
Would you be able to do it?
Partially.
Okay. Try to do it fully, and once you do it, you have solved the Navier-Stokes equation. So you've gone through each of the steps.
I solved it. I just I just didn't add the plot names into graphs. I was too late to do it.
No, that's fine. So as long as you know how to solve everything, that's perfect. Okay, so I will show you. Okay, some people ask about bugs. Things don't work and things didn't make sense. So if you want to debug your program, the easiest thing to do is first check if the divergence of your velocity field is 0. Okay, so I'm just going to plot the divergence of u. Okay, and you see this is 10 to the minus 15 everywhere in the domain. And if this is not true for you, something is wrong. Okay, so that's the first check. Second check is you do only diffusion. So you run the whole code doing only diffusion, no pressure projection, no advection. So yeah, advection commented out, pressure projection commented out. And then what will happen is your velocity vectors will just decay, right? The third check is with this diffusion only simulation, your divergence you should stay 0 for all the time steps. Okay. Now, when we start doing advection also, this statement will no longer be true. So now the divergence of u will not be 0 anymore. So let's see when we plot this. All right, so now div u is no longer 1e minus 15. Okay, and we expect that because the advection term introduces this non-zero divergence. And the pressure projection is what will correct it. Oh, by the way, let's see what happens to the velocity vector if we let it run without the pressure correction. This is another simple test. So let's see. All right, the velocity field gets messed up, does not look like a Taylor green vortex anymore. Okay, let's bring back the pressure correction. And now the code will be much slower because we have to solve the Poisson's equation. All right, and there. So it's much slower, but it retains its Taylor green vortex characteristic. And again, it will decay, and you have the analytical solution to compare to whether your solution is correct or not. And that the full solution actually looks like this. So here I'm comparing numerical answer to the analytical answer. And you can see some difference, but overall, very good match. Okay, so those are the steps you can follow to check each part of your code. And again, please do the spot survey if you haven't already done so. So it's just spot.fau.edu, and it's a very quick thing. So it's again very good feedback for us to improve the course in the future. Right? Okay, we have one more person in Bucarato. All right. Do you have? Wait, is that so? Okay. Do you have any questions about the project? No. All right. Good. Okay. Perfect. So today, let's talk about turbulence modeling and what it exactly means. So if I asked you to do a simulation of flow around a ship or flow around an aircraft, what would you do? What would you say? What would you do? If I say, go simulate this big oil tanker.
Click turbulence and after that SSDK omega without more functions.
All right. So,
and run it.
yeah. Click a bunch of buttons in ANSYS Fluent and what would you do? What would you do? If I said simulate flow around this supertanker. Yes, I'm asking Sumi.
Yeah, so it would be computationally very expensive to use simple DNS direct numerical simulation. So I will use mostly what industry would do, like RANS simulation, or LES would not be feasible even. So yeah, RANS is the optimal
Okay.
substituent to.
Right. So the first thing you should tell me is you're crazy. This is not possible, right? It's not possible to do an accurate simulation of these things. And the reason is exactly what you're saying. DNS will not be feasible. We cannot resolve all the length scales going from all the way from the large scales to the smallest scales in these flows, right? So what do people do? How do they study turbulence? Do you know?
For around these aircrafts, yeah, they will use some turbulent models for like RANS models or LES models. LES models, I don't know if even LES won't be very feasible in such scenarios, but yeah, RANS models would be.
Yeah, so they use some models, but where do these models come from?
So, approximation.
The models come from theoretical arguments or from very simple experiments. Okay? So these are very complicated, but people generally tend to use very simplified configurations to actually start looking at what potential models could be used, why they could be used. Okay? And the simplest case is called homogeneous isotropic turbulence. So that, right? And I'll write down what each of those terms means. So this is basically doing simulation in a 3D periodic box. So all the walls are completely periodic. What goes out here comes back from the other side. And we're looking at mixing of a passive scalar in a turbulent flow. This is the simplest thing you can do. At a higher level of complexity, we can go to using simple wall-bounded turbulent cases. Okay? Here we have a flat wall, and we have turbulent flow over it, which we can study. And the argument is that no matter whether you have a car or an airplane or a ship, all these complex surfaces look like more or less like a flat surface, at very small scales. So if we understand what's happening at very small scales, if we are able to control that, we can influence the entire flow field. Okay? And that's the basics of turbulence modeling. That's the basic idea. Okay, let me just write down a few things quickly. Simplified configurations for studying turbulence. Okay, and the first one we looked at was HIT, which is homogeneous isotropic turbulence. And everything I'm mentioning, I'll mention very superficially. People spend their lifetime studying just this. Okay? So this means space does not matter. Okay, so if we go from x1 to x2, the statistics will not change, right? Isotropic means direction does not matter. Which means whether we look at statistics in x Y or Z, we expect them to be the same. So everything is radially symmetric. Okay? So this is the simplest configuration, and we have a 3D periodic box of turbulence. Okay, and this is the simplest one. All right. The next level of complexity is the channel flow, and which is what I was showing you, the black flat plate with flow over it. Okay, and the advantage of this is, you have two walls, and the walls are responsible for creating the turbulence. Okay. So this gives you a physical mechanism for creating turbulence. So advantage is physical mechanism, which is the wall or generating turbulence. What's the disadvantage? Disadvantage compared to the periodic box case. Can you think of any disadvantages? Think computationally, think coding. 3D periodic box. It's very, very simple to code, right? There's no boundary conditions, nothing complicated going on. With this, now you have to take care of what happens at the walls. So, boundary conditions, more complicated. And another disadvantage is the small scales close to the wall are very important. So you have to resolve these small scales. In the 3D periodic box, you don't care. There's no wall where you have to put down more grid points. So this can be computationally more expensive. Okay, and this is called, in the channel flow, we have temporally developing turbulence. Which means that you might start with an initial nice laminar flow, and slowly it will get turbulent. Another configuration is the boundary layer flow. Okay, so in the channel we have two walls, and in between there's flow. With the boundary layer we have a single wall, and there's flow over it. Okay, and slowly the boundary layer will develop and become turbulent. And this is spatially developing turbulence. That's because, in our simulation, we just have the wall and there's incoming flow is uniform, or you might impose some turbulent conditions. And slowly, as we go along X, we see the boundary layer becomes turbulent. And the advantage is, this is the closest configuration to real external flows, right? So this is the internal flow inside a pipe, for instance, an air conditioning duct. And this is what you would get when you're looking at flow over a car. And disadvantage, what is the disadvantage? think about, okay, here we have periodic flow, whatever goes out comes back in, so I can technically have a small domain. What happens here? There's no coming back, right? So if you want to look at a large Reynolds number, REX, you have to have a very long domain. Make sense? So this can be, this configuration tends to be the most expensive. So these are three major turbulent flow configurations that people use to study what's happening at the very small scales. In simulations at least, and in experiments. And the goal is to try and understand what's happening physically, so you can postulate models that might work. Okay. Models. What do these models do? Let's think about that for a second. Okay, so do you remember what is the problem in turbulence? Why can we not simulate high Reynolds numbers? No. If I say simulate something at Reynolds number 1 million, what would you say?
I would say I need a turbulence model.
All right, yeah. Why do you need a turbulence model?
Because it was chaotic, so the source of that fluctuation cannot be predicted in high Reynolds number.
It cannot be predicted, but it can be simulated, right?
Yes.
We are solving the conservation laws exactly. Exactly. We are simulating them. So technically, you could just simulate it. Let's solve it numerically. That's what I'm asking. So if I say solve this numerically, your answer should be you cannot do this because go on.
So the nonlinearity prohibits me from solving at very high Reynolds number. Moreover, the number of scales I have to resolve grow too much at very high Reynolds number. So that's why.
So so you guys mentioned machine precision that goes to nonlinearity, which leads to unpredictability. That's the unpredictable behavior, chaotic behavior. And the more important point is the length scales. If I'm able to resolve all the physical length scales, then that's fine. Then I can give you the correct simulation. But that is the biggest problem. So high RE means a large range of length scales. Need to be accounted for. Okay, and typical separation is typical range can be from 10 to the 6 to 10 to the 8. In a moderate Reynolds number. What does this mean, 10 to the 6? It just means the largest eddies are of size, let's say 1 kilometer. And as they break down and start dissipating, the smallest eddy size might be 1 millimeter, right? So that's 10 to the 6th order of magnitude separation. And our grid scales, when we discretize the domain, the delta x and delta y have to be small enough to resolve this 1 millimeter. Okay, it's the same problem we see in experiments. There's no way to have enough points to resolve everything that is 1 millimeter small and do that for 1 kilometer by 1 kilometer by 1 kilometer. Okay, so resolving the small scales is the biggest issue. Okay, and now let's talk about the spectrum. Okay, let's see where it'll be clear how exactly this is relevant. So energy spectrum, E of kappa and kappa. So in turbulent flows, the E energy spectrum looks somewhat like this. Okay, so do you remember what kappa is? How is kappa related to these eddies I'm showing here? Think in terms of the wavelength. Okay, wavelength in space. Kappa is, let's say 1 by lambda, right? Or 2 pi by lambda, whichever one you prefer. And what would you say the wavelength of this eddy is? I'm using the term wavelength very loosely. What's the periodic length of this eddy?
1 kilometer.
1 kilometer, and this is 1 millimeter. So where would this go on the energy spectrum? To the right or to the left?
To the left.
So the large scales go to low wave numbers. Okay? So let's see. These are the large eddies. Okay? And these are the small scales. Make sense? High wave number corresponds to the smallest eddies. Okay? So what this picture is telling us is the energy contained. This is actually equivalent to looking at kinetic energy. So this is high kinetic energy, low kinetic energy. The energy contained in large eddies is high, and what happens slowly is these large eddies start disintegrating, and there's an inviscid cascade. And that's what we were talking about earlier. So there's an inviscid cascade. Up until the eddies become small enough that you can start dissipating. Okay. So energy is destroyed here. Destroyed at these scales due to viscosity, and energy is injected into the flow here. Does all this make sense? Something is confusing.
How do you define E?
Ek, you can just say, is the Fourier transform of half u squared. Okay? That's why it's called the energy spectrum, kinetic energy spectrum. So it's basically the kinetic energy. Anything else? Okay. All right, now we were talking about this typical range being 10 to the 6 to 10 to the 8. We cannot resolve all the length scales. So in terms of this spectrum, what does that mean? Up to what point can I resolve and what is unresolved? You know, almost always the large scales are very important to us. This might be a hurricane we want to track. This might be the large flow features on a car or airplane that we care about. So which half, so left half or right half of the spectrum must we resolve? It's of physical interest to us.
Left.
Yeah, so the left half, right? So everything from the large scale up to a certain point. And that certain point is dictated by how much computational power you have available to you. Okay? If you have a huge supercomputer and you can do very small delta x's, potentially you could resolve all the way over here. Okay? But for real cases, that's not the case. We are stuck to somewhere over here. Even for the simple configuration we were talking about earlier. The wall-bounded channel flow or the boundary layer. So what the spectrum looks like in these turbulence modeling simulations is, you have something like this, and then what happens? By the way, before we go on, this is called a DNS. DNS is a dialect numerical simulation. And the only thing that this means is all relevant length and time scales are what? Are what? Are absent from the simulation, or what does DNS mean?
Are included.
Yeah, they're included, they're accounted for by the simulation. That's it. That's the only thing that DNS means.
Excuse me, why this curve starts is like parabolic?
Where?
Why not linear? Yes.
Here?
On the left, on the far left, is going up and then down.
Why is it going up and down?
Yes.
So, again, think about a car, for instance. Okay? When you drive, you are injecting energy into the flow at the length scale of the car. Okay? So you're injecting energy here. That's all you're doing. But what happens to that energy? The flow does not disappear immediately. These large eddies will start breaking down, and the energy starts decreasing slowly. There's no energy destroyed over here, up until when the eddies are small enough that viscous dissipation destroys the energy. That's why you first go up and down.
Yeah, I understand what you're saying, but in the physical, for example, in a wave, where is that start point, that injection?
So for a
Where does
wave,
that correspond to?
who is creating the wave? A cylinder is creating the wave. So this length scale would correspond to the diameter of the cylinder, for instance. Make sense?
Yes.
Okay. In the end? All right. So, okay, in a turbulence model simulation, what will the spectrum look like? Yeah.
It would drop at this last wave number, the highest wave number.
Where should I put the highest wave number? Should I put that here?
Yeah, like it will depend till what I'm, what all scales I'm trying to resolve.
Okay, and why will it drop?
Because there are no such scales there, so there won't be any energy associated with them.
Well, it will not drop. I mean, think about the delta x. So this is, let's say it's 1 by delta x, right? And this is your grid size. You can compute energy for this length scale, but smaller than that does not exist in your simulation. So all of this is unknown. And this is exactly what these turbulence models do. So this has to be modeled. And this is called resolved. Okay? And the important thing is, if you don't do anything, if you just say, my grid is 1 delta x, I don't care, let me just run the simulation and see what happens. What will happen? And remember, your cylinder is injecting energy continuously. We talked about this is an inviscid cascade, so there's no destruction of energy. If I remove the energy destroying scales, what will happen to the simulation?
Yeah, horizontal line.
No, this is like a single time snapshot. Okay, so I compute the energy at all the scales at a single time. So as time passes, what will happen to the curve? So what happens is you keep injecting at this scale. It keeps flowing down to the smallest resolved scale. And then it has nowhere to go. There's no mechanism for dissipation. So the energy will keep piling up over here. Okay, and then your simulation will go unstable. That's the issue with turbulence simulation. This is what turbulence modeling tries to resolve. Is this clear? Conceptually. Okay, so that's it. Conceptually, that's it. But again, you can spend multiple lifetimes going through the literature that people have published on these things. Okay. All right. So we need some way of dissipating this energy. What would you do? Think about the Navier-Stokes equations. How can we change the momentum equation to do something about this pileup?
Adding a term, it was like lost term or kappa.
Adding like a diffusion term,
Yeah,
right?
it can be diffusion.
Yeah, something that destroys energy, something, right? So that's exactly what turbulence models try to do. So let me write down the Navier-Stokes. So we have these. Okay, so this is the normal Navier-Stokes. But what we are doing now is we are not solving for the true velocity. We are solving for the filtered quantities, right? What does this mean? It just means the real u is equal to the filtered u plus the fluctuation. So this is called, well, this is the fluctuating velocity. The actual term is called sub-grid scale velocity, okay? Or SGS, okay? And this is the filtered velocity. What do we mean by filtered velocity? So, in reality, if I have a highly turbulent flow, the velocity would look like that, right? What does U bar look like? What would U bar look like? Just intuitively, what would it look like? Flat. You want to average out everything. Yeah, so you can do that. Say, okay, this is my UR. This is called this is averaging, basically. Okay. Or you can do something less drastic. Right? Again, think about the delta x we need to represent the blue curve versus the black curve. If we don't have very small delta x, all these high frequency fluctuations will be lost. But if we say we only care about the filtered velocity field, the blue curve can be represented with much larger delta x's. Make sense? So this is the argument people put forward, that not resolving everything is equivalent to, mathematically equivalent to doing a filtering operation. Something is not clear.
Looks clear.
All right. Clear? All right, okay. So, great. That does not resolve the small scale fluctuation acts as an implicit filter. Okay, and there's a lot of controversy on what exactly is the mathematical representation of this implicit filter. Regarding how to represent this implicit filter mathematically. All right. Let me point out this. What we have written here is still incomplete, so we will come back to it and see what's missing. Right? All right. So there's a lot of controversy about. I say I will not resolve all the scales. What exactly does this mean? Are you familiar with explicit filters? Have you heard of the Gaussian filter? All right, you have not. Have not. Do you know what this one is? Gaussian filter. Yeah?
I don't remember.
No? So there's several types of filters in this one. Gaussian filter, box filter. These are the three main and simplest ones. And there's one called sharp spectral filter. Okay, so the box filter basically looks like a box. This, and you do averaging. So you add, let's say you sum up your 4 neighboring points, compute the average, and store that at your node. That's a box filter. Gaussian filter is doing the same, but with a Gaussian kernel. You take your own value, multiply it by, let's say, 0.5, if this is 0.5, take your neighbor, multiply it by 0.4, and then sum it up and store at your own location. What this operation basically does is it smooths out the field, right? So if we look at, let me see, perfect. So this, mathematically what we're talking about, if you do this practically, this is exactly what happens. Originally you might have very sharp lines, and when you do the Gaussian filtering, they get blurred out. You do it, if you do it again, it will get more blurred out. And depending on what the standard deviation is, you get more blur or less blur. So that's it. And now you can see how that's related to our velocity field, right? The sharp lines get blurred out, and we get the blue curve. Okay. So that's the idea, that if we do this sort of filtering, we can talk about what the large length scales, how they evolve in time. Okay, so this was incomplete. Let's make this complete now. And the main question is, what do the filtered Navier-Stokes equations look like? Okay, and for that, what we do is we just take the momentum equation and apply the filtering operation to the whole thing. Okay, and we do a filtering operation to the whole thing. In practice, what you would do is, if you have DNS data, you would take it and convolve it with these Gaussian filter, box filter, or the sharp spectrum. And okay, what's the result? This bar I can take inside here. This bar, what can I do? Can I take this inside to each of them? Let me change this to nabla form, right? So it's nabla dot uu. Okay, and this is because this is equal to u nabla dot u plus u dot nabla u, and this we know is 0, right? So these two are equivalent. U dot nabla u is the same as this. So I've just changed this to this. For minus nabla p, we can take this inside, plus u nabla squared u, we can take this inside. We can take this filtering inside because this is linear in U, but this term is not linear in U. Okay? So we cannot just say this is not equal to nabla dot u bar u bar. Make sense? When filtering, this operation is not valid. This left side is not equivalent to the right side. Okay? So, should we be happy with this Navier-Stokes equation? Does this make sense or not? Something missing? Think about when you're solving on your course grid, what are you solving? Which of these quantities are you solving for? Are you solving for U or U bar? Does the question make sense?
So we're solving for U.
You would be, you're saying you're solving for U, not for U bar. The grid is coarse, yes. So you cannot resolve all the scales. You can only resolve up to some of the scales. So you're actually solving for U bar, right? The filtered U. If we go back to this feature,
okay.
Right? So you're solving for the blue line, you cannot resolve this. So if you're solving the Navier-Stokes equation without worrying about turbulence modeling for the filtered U, what would it look like? It would look something like this. Then U bar, then T plus nabla dot. Right? So you would solve something that looks like this, correct? But our original Navier-Stokes equation is this. So there's some terms that are missing. So I've added this here, let me add that to the other side. Okay, and let me bring that to that side. Now this equation is exactly equal to this equation. Make sense? These equations are the same. So this is the true Navier-Stokes equation, which I'm applying filter into, and this is what it ends up being. Okay. Again, cancel this, take this to the left, you recover that to the left. So when you solve your equation, you're solving for this, and this is the term that is missing. This is called the subgrid stress. So this term is, you can write it in as, people usually write it as a minus. Minus u bar, minus u bar, u bar. Okay? This is called the subgrid stress, tau SG. Okay? And this is the term that has to be modeled. That all of them, no matter which one, all turbulence models try to account for. Is this clear? This is what turbulence models do. There's a missing term in the Navier-Stokes, in the filtered Navier-Stokes, which they try to recreate. And the problem is fine in your simulation. You might have u bar. This term is present, but this term is absent because this involves the full u. Clear? All right. So some models that try to do this. All right. So first, we go from DNS to LES to RAND. Okay. DNS we already know is direct numerical simulation. No model required. LES is large eddy simulation, which means that if you look at the spectrum, you resolve up to some large eddy, and we have cutoff, and all of this needs to be modeled. RANS means Reynolds averaged Navier-Stokes. Okay, and you might have heard of RANS quite a bit. Most industrial work tends to use this RANS. Why? Only the mean flow is simulated. Okay, which is equivalent to saying all the length scales, all the small length scales modeled. Okay, here you were actually resolving up to some small scales, but now you said, nah, I don't care about anything. Let me get rid of everything, I only care about the average flow. So, why does industry prefer this? Think about it, computational. Here you have to resolve some things, you need some heavy computation. Here, you're just solving for the mean flow. You're solving for one wave number, kappa equals 0. So you can do that simulation of an airplane on this laptop in a few minutes, right? So that is the point when CFD starts becoming colorful fluid dynamics. Okay. So yeah, I mean, university research almost never uses RAS. Industry has to rely on it because we haven't given them a good turbulence model yet. Okay, so these things are used a lot, but you should always be skeptical of how accurate the results are. Do you know some of the model names that these? Okay, let's start with some LES models. LES models, a few of them, right? Yeah, I heard. Okay, I heard Smagorinsky. Do you know what Smagorinsky model does? This was created in 1967, I think. 60s for sure. Do you know what it does? Okay. You said Smagorinsky, so do you know what it does?
Yeah.
Based on some length scale you are giving in the simulations, students.
Physically, what does it try to do?
Oh, okay. I know mathematics.
No? Alright. So think about what happens here. You said we should introduce some dissipation here. Right? So Smagorinsky model does exactly that. It says this unknown term will look like a viscous term. Okay? So this says tau SGS will look like minus 2 mu SGS S. And this is basically half of nabla U filtered plus nabla U filtered transpose. Make sense? So this is just saying, all right, I have my physical diffusion. Let me pretend this additional term also acts like a diffusion. So that's the term I will use. And this is a very popular, still used LES model. Although there have been numerous papers showing that this is not the best way to go. Okay. Again, people have to use these because there's nothing better that exists. So there's this Smagorinsky model, and all right, here the unknown is this, right? So this is a constant model coefficient. How do you determine this? How do you say, for my simulation, mu is equal to blah, blah, blah?
Probably,
Once more.
probably according to the volume. Or
Volume.
you're giving you cell size.
You what?
You're giving the cell size probably. Or something depending on the cell size.
Yeah,
I don't know,
but
or something.
you're already more sophisticated than what they did. They said we will fit experimental or DNS data to figure out what this mu is. And then the mu was a constant between 0.1 and 0.24 or 25. Okay? And people keep tuning the value until they get the result they want. How do they know what result they want? Because there's a DNS that exists. So if you try to do something that doesn't exist, you don't know what mu should be. That's the biggest problem in turbulence modeling. It's not predictive. Okay? Anybody that tells you otherwise, again, be skeptical.
What is the meaning of it, this mu? Physical meaning of it?
Mu is like an additional dissipation term. So here we have, you can divide this by rho, right?
Yes, I know, but
It's like a model dissipation that kills off the energy that will accumulate over here. Make sense?
yes.
Basically, it does that. Any other question?
I'm comparing this with the viscosity of a fluid, for example.
Yeah.
That is property of a fluid.
Yes.
What in this case is a property of a
This is the property of your model.
Model.
Yeah. And this should depend on how much energy is piling up here that you need to get off, cut off, right? So when you change the flow conditions, you will have to change mu. When you change it from a homogeneous turbulence to a wall-bounded turbulence, you have to use a different mu. And there, mu dissipates too much, so you have to lower the value to 0.1 arbitrarily. Okay? And all of this, how do you know it dissipates too much? Because you have DNS data to compare to. What if you want to do a simulation for which you cannot do a DNS? You can forget about it.
And if we have DNS, why would we do Elias?
Exactly. So these model coefficients are tuned at very low Reynolds numbers, for which you can do DNS. Okay? So you do a DNS and say, okay, for this low Reynolds number, I have this particular value of mu. And I'm hoping, I'm praying that this remains valid for millions higher Reynolds numbers, which again, never works. Which is why we don't have good turbulence models. Make sense? All right. So there's the Smagorinsky model, there's the dynamic Smagorinsky. There's the tensor diffusivity model. And this tensor diffusivity model just says TSGS is equal to, let's say, CSGS times U bar bar whole thing minus U bar bar. Okay, so this is made to look very close to that term. But again, there's an assumption. We replace this true velocity with the filtered velocity. Okay. So again, there's no good way to do this. And there's RANS models, and again, there's many, many more. Some RANS models that you might have heard of are K epsilon model, K omega model. I heard the Palmaras model. What was one more? Did you say something else?
But we have SSD, RNG.
Yeah, there's
SSD
SSD,
omega.
RNG, yeah, SSDK omega, etc., etc., etc. What do all these models do? They try to include the influence of this term in the filtered Navier-Stokes equations by fitting data to experiments or keep modifying the models, keep tuning them until you get the result that you expect. If you already have the result you expect, you don't need to do simulations, right? So that's the state of turbulence modeling today. Questions? And people are still trying. They have been trying for 60 years. So I will put in some final remarks, and yeah, these topics still generate a lot of fighting at conferences, and actually I've heard people shouting at each other. I've seen them shouting at each other. So words of caution. At present, no good turbulence model exists that can be applied to general flow configurations. Okay? So anytime you use LES or the RANS models, what should you do? What?
You call this approximation?
Use different models, check. Compare different models.
Compare different models, but how do you know which model is correct? If you already have the answer, which you can compare to, then why do the LES or why do the simulation?
But experiments can take time.
Experiments can take time, yeah. But you have the experiment at the flow condition you want, right? Why do you want to do more experiments? Because you want to change the Reynolds number, or you want to change the cylinder. In that case, the model coefficient also needs to be changed. So, no predictive power. Do you get what I'm saying? Yeah. So, again, people might yell at me for saying that, but this is the truth. What? No. If you talk to a researcher who spent their lifetime in turbulence, they will start screaming, literally. But that's the truth. Yeah.
There are 10.
What?
10 each coefficient nearly for Ross models. So every time you change the coefficient, the simulation changes.
Yeah, every time you change the coefficient, the results will change. And fine, you can keep changing the coefficient until the results match your expectation. But if you already have an expectation, there's no need for doing a predictive simulation. That's the purpose, right? The simulation predicts something that's correct that we don't know. That's the reason for doing simulations. Make sense?
Yep.
So again, there are limitations to everything, to experiments, to simulations, to modeling. Just be aware of that. Okay, anytime you use LES or ANS models, be aware of the limitations. Okay? And be skeptical, always. CAL?
CAS.
Yeah. Yeah.
Okay. Question is, let's say we have thousands, millions of papers in the world, right?
Huh?
Some of them, for example, uses some turbulence model for some application. Okay, I will give you some example. For example, it says I use SSDK omega model. This was my ship, and it worked, and I compared with the results, and it matches. Okay, and some of the paper uses some other turbulence model, and it says, for me, this model didn't work, but I use the same simulation.
Yeah, and that's a very common situation. If you give the same, if you tell 10 different people to use the same model, well, yeah, the same model and do the same simulation on the same geometry, they will come up with 10 different results. And there are workshops that do exactly this. There's a big problem given to 10 different groups, research groups, and then they all come together and compare. Nobody matches each other, even if they're using the same thing. Okay, so that's why I'm saying be very careful and be very skeptical, always. If you want my unsolicited advice, never use trans models. They take more time they take a lot of your investment and the return is not good. So, yeah. LES models, again, they're expensive, but they give you some, they're closer to the truth than RANS. RANS is completely easy. All right, let me get rid of everything, just solve for me. Okay?
Okay, but the problem is the industry comes here and submits a project, and let's say it's 30-meter ship, and you can solve with this LES with the limited computer resources.
No, so that's the point. You tell them what can be done and what cannot be done. And if they just want colorful pictures, then,
Generally, yes. If you're talking about industry, they want.
Yeah, then why come to scientists? So that's not why we're here.
I'm questioning for one.
Okay, so anytime you use these models, be aware of the limitations and be skeptical. And finally, you can trust DNS results, provided what? You can trust that provided.
What do you mean provided?
On condition, you should only trust DNS results once you know that you have resolved
All length scales.
you ensure that all length and time scales are resolved. That by definition is the meaning of DNS.
What about
And again, you can compare your simulations to experimental data. You will get a very nice match.
What do you mean? This DNS result is trigger is inherently is.
That's what I'm saying. So sometimes people forget to do grid convergence. So you have to do a grid convergence analysis to make sure you have resolved all lengths. You have to do time convergence to make sure you have resolved all the time scales. Okay? So you have to make sure of these things. And then you can be confident of the result. Okay? But again, and you have validated your code. Validated / verified your code. What does this mean? When you solve, when you get a numerical answer from your code, the first thing you should do is try to solve a problem for which you know the analytical solution, which is what we have been doing in all the homeworks and projects. There's always the analytical solution given to you, and you're always told, compare your result to the analytical solution. It's a very important part of writing any code, validation and verification. Because a single minus sign misplaced can destroy your results. Okay? So as long as you make sure you resolve time scales, length scales, you validate and verify your code, you can trust your DNS results. RANs and LES are still topics of very heavy research. Very, very heavy research. They are the most active areas in fluid mechanics. And again, if you want to spend a lifetime on it, you can. Okay? So any questions?
We didn't talk about real stress and
The RANs?
real stress models.
Yeah, so
And that DES.
okay, so what DES does is it uses RANs far from the walls and LES close to the walls. Okay. And Reynolds stress models, what do? They just they again basically try to model this term. Okay. So again, there are details which for me are not, at least for CFD plus, are not worth going into. You can ask me later, and anybody can ask me later. I've tried to avoid any of my time spending studying RANs, because again, I'm a firm believer in we should not use this. But yeah, that's an opinion, that's not fact. Anything else? No? All right. So projects are due next week, please. It's already very late. Start and email me as soon as possible. Don't email me next week. I'm stuck and it's due tomorrow. What do I do? Okay. So awesome. And don't forget to fill out the surveys. All right. So that's it. And we're done.
So if someone submits, I didn't like the instructor after 2 months, 2.5 months.
What?
If someone says I don't like the instructor,
That's fine. That's a valid feedback. That's a valid feedback.
It's recorded.
Yeah.
you are recorded for the first.
No,
10 minutes,
you
so
don't.
were not
You don't
recorded.
just say you didn't like it. You say why you didn't like it, so I can fix it. Okay. So otherwise, what do I do?
We need guilt.
You need guilt.
Guillotine.
Oh. Then you have to find a
advisor.
No.
That's the state of turbulence. Not very good. It has been like that for decades.
So what is the active research specifically right now?
LAS. LAS and RANs. New models, better models, that's all.
Check International Computational Dynamics Conference.
So why don't you,
It's all LES.
do you want to research in this field, the turbulence?
No, I did that for my PhD.